Hello, this is a module 3 investigation 1. So in the module 3, we are going to talk about the polynomial function. So we're going to start with the box problems and the modeling relationship. So number 1, consider what is involved in building a box without top from the 8.5 inches by 11 inches sheet of paper by cutting square from each corner and folding up the sides. So if you look at the piece of paper and then becomes the box. So in the piece of paper, the side of the whole page, the piece of paper is 11 inches as a length. And then the pieces has been cut it out at the corner, right? And then becomes a 3-dimension, which is a box we have here. Okay. And then also the 11 inches, which becomes the smaller than the 11, of course, in the box. So the amount of this pieces becomes this here. And then the size of this much becomes this one in a box. Okay, and then that one, I can say this is the length of box. And then the other one is, I can say the width of the box. Okay, and then of course this much is a height of box. Okay, so to understand how the quantities in the situation are related, it is important to find the situation by doing the following. So number 1, cutting 4 equal-sized squares from the corner of an 8.5 by 11 inch sheet of paper, and then the folding up the sides and taping them together at the edge to make the 3-dimension as a box. So do cut out the hat to be the square? I want to say yes, because what if it's not square, which means if you say, okay, there's a piece of paper and then you cut it as the rectangle. Okay, of course this has to be the same the 4 corner, right? Same size at the 4 corners. And then what happened is, if you're making a box, as you notice, maybe we'll get this much, right? And then as so this has become the length of the box, and then width of the box must be this one. So width of the box very narrow, and then if you actually on the height from that I put will be the higher than the on this side. So which is you're gonna get this kind of forms, which is, it's gonna be very low to get this. So if I put it in, so this doesn't make actually nice box because it will give you the different height. So the box have a different height. So it has to be the square to have a same height of the box, which is, you can think about it, this is kind of increasing, right? This is much is increasing, and the other side is not. Okay, so all right, so let's talk about C. So what quantity is in this situation vary? So we are talking about varying quantity. The quantity is kind of varying. So because of the cutout at the corner, the cutout getting bigger, and then the length length of box will be changed from the bigger from the to the smaller, and also the width of box will be changing from the greater to the smaller if the cutout makes the smaller pieces to the bigger pieces. And then it will change the volume too. And also surface area too. But what could be the constant this time? But constant is I think it looks like everything changed by the cutout. So I don't think anything as make a constant which is stay the same. And D described how the configuration of the box changing as the length of the side of the square cutout vary. So if the small cutout gonna give the box box will be very short box, flat and short. Because cutout is a small means well you have a very flat ones. Okay. But then the box is getting the tall and then thin box. Okay, so which means this. If you cut up big and then your box maybe this. Okay, so it doesn't look nice. So when you have let's say this much, right? So yeah, this kind of boxes I'm talking about. Okay, so it's from the flat to short to the tall and the thin because height getting bigger and bigger of the box. The E, use the volume with cubes. Animations described how the volume of the box varies as the length of the side of the cutout varies from the 0 to 4.25, which is we have to actually you have to use the animation. So I wish I can show you here. So hopefully I can show you in the what we do the Zoom meeting. So yeah, we see that. And then it actually makes a difference, okay? And then the F, based on the response to part E, and then sketch the graph of the volume of the box with respect to the length of the side of the square cutout. So one side, I want to put that as the length of the side of the box. The length of the side of cutout. And then the other side, I put that as the volume of the box. So for the length side of the cutout, I want to put that as every 4 is 1. So 1, 2, 3, and 4, maybe 5. And as a volume, I want to make that as every every 2 is a 10. So 2, 10, 20, 30, 40, 50, and 60, okay? Then 20, 30, 40, 50, 60 on the horizontal side. I want to say 3, 1, 2, 3, 4, 5 as the inches. So now you just need to see what kind of formulas we have to actually define that, okay? So the volume of the box is going to be the length and width and height. So length is going to be it depends on the cutout as H, okay? So cutout, let's say H is X. So if you look at the side of the paper, there's a 2x is going to be the cutout. So there's a 1x and 1x and 1x here to here too, right? So from the length is going to be 11 minus 2x will becomes the length of the box. The width also from the 8.5 minus 2x, but height stays I call that as x. So this is x representing the it's going to be a height, also the side of the cutout. So if you plug it in a 0, and then you get the, of course, is a 0 box. And then when you plug it in 0.5, which is about here, it becomes a 3.75. So 3.75 means about here. And then if you use a 1, cut out 1, it becomes a 58.5. And then if you have a 2, plug it in to get 63. And then if you have a 3 inches cut out, it'll be the 37.5. And then cut out 4 becomes, cut out 4.25 becomes a 0. So which is 2.5 right here. So if I connect them as a curve, so yeah, put it together and then connect them nicely. Okay, so this kind of, so this is not parabola because when you actually multiply them out, it becomes x cubed. So this x times this x times this x will becomes x cubed. So this is actually the cubic functions. So this kind of graph you'll get. And then use a ruler to measure the length of the side of your square. So now you have to actually try to make one for you to see. So you need to decide what cutout the length you want to choose. But you can cut it actually as a length of box. Okay, you can cut out more than a half of 11, right? Because if you cut out more than 11, half of the 11, and then it won't make a box at all. Okay, so you have to say the length must be, the cutout is the half of, so it has to be the whatever the length of box has to be the less than 11 over 2. And also the width of box, also I want to say length is L, and the width of the box must be the half of 8.5 over 2. But in order to do that, actually if you put the 5.5 from the length, and then half of 8.5 divided by 2, which is 4.25. So if you cut out more than 4.25, and then it won't be the make a box either. So we this is what we needed. This is actually the more important. So the cutout, which is the side, should be less than 4.25 this time. Of course, the gradient. That's why 4.2i end up with a 0 volumes, okay? All right, so let's look at the next page. So in the next page, in number 2, now I am using the formula for here as a volume will be the length, which is 11 minus 2x, and 8.5 minus 2x times x for the h. So length times width times height. So let x represent the varying length of the side of the square cutout in inch. And then let W represent the varying width of the box base in inches. And the L represent the varying length of the box space in the inches. So let V represent the varying volume of the box in cubic inches. So we want to fill the tables in. So whatever given, we can find this. So if I individually write down the formula, so length is actually 11 minus 2x. The width is the same as 8.5 minus 2x. The height is the same as x. So x is given, which is we don't have a height. Height we use as an x. So width is, if you plug it in 0 here, it becomes 8.5 and then 11, but there's no volume because the height is already 0. So 0 times going to be everything going to be 0. Then now the second row, the width is a given. So if you use the width is here, So in order to solving that, you plug it in 6.5 into the W, and then you need to solve for x. And then that's the case, you're getting a 1 for x. And then once you find the x, you can plug it in here to find the length, which is going to be 9. And then the volume now you're going to get as 58.5. And then the third one is x is a given, so just plug it into the x place, the length and width. And then the 4.25 give us the 0 width, but you still have a 2.5 as length, but still the volume going to be 0. That's a more important. But for the next row, the width is already 5, which is I said x must be less than 4.25, right? So more than 4.25 can get any of the volume, so that's impossible to make. So once it's one side is impossible, you don't have to worry about the other. And then the length is now 15. So when length of 15 means you plug in 15 here. And then so for x, which is x becomes actually the negative, which is impossible too. So impossible side cut out. And then same thing as a 2, which is length is a 2. And then if you can get 2 here, and then let's actually figure it out. So 2 equal to 11 minus 2x, and subtract 11 both sides. Negative, actually the 9 equal to negative 2x is x equal to 4.5. So x is a 4.5, but if it's a 4.5 in the width, and then it's not going to be it's going to be a negative. So the width is impossible this time. You can have a negative length for any of the side. So B explained how the length of the base of the box is related to the length of the side of the square cutout, and how the width of the base of the box is related to the length of the side of the square cutout. So I already explained as a formula though, okay? So length of the base is always 11 inches minus 2 times of the length of the side of the cutout. Also, so length of the box always the 11 minus 2 times of the length of the cutout. And the width is always 8.5 minus 2 times of the cutout. So the C, define the formula to determine the width of the box in terms of the length of the side of the square cutout, which is, I already did it. So width gonna be the 8.5 minus 2x. And then define the formula for the length of the box, which is gonna be 11 minus 2x. And define the formula to the volume of the box. Is the volume gonna be length times width times height, which is the length is 11 minus 2x times 8.5 minus 2x, and the height I call the x. The F, use the formula from the part E to represent the volume of the box when x, the length of the side of the cutout, is 0.5. So in order to find the volume with the x is 1.5, so I got 11 minus 2 times 0.5 times 8.5 minus 2 times 0.5, and then times by 0.5. And then you'll see the volume. Okay, and then they use the formula from part E to represent that the length of the cutout is now 3. So now the volume becomes 11 minus 2 times of 3, 8.5 minus 2 times of 3, and then times by 3. And then that will represent the box. So now number 3, I think you can do easily. Okay, so the cutout length is given as 1.5 and 2.7, 3.8, and 4.2. And then you look for the volume, which is to plug it in. So when you plug it in, the 1.5 into actually you gotta use the letter E. And then when you compute that, I got the volume of 66 and 46.87 and 11.62, and then the 1.09 is the volumes. All right, let's look at the number 5 right now. Okay, so number 5, using the graphing calculator, solve the length of the side of the square cutout if the volume of the box is 62.5 cubic inches. Okay, so even though they set it at the graphing calculator, right? Which means I think that you better use the graphing parts. So this is actually the problem for the volume of is 11 minus 2x times 8.5 minus 2x times by x, right? But this time, the given is the volume. So you have 62.5, 11 minus 2x, 8.5 minus 2x times x. So in order to find that x, we have to use a calculator to see what x of the value get close to 62.5. So if you use a graphing calculator, what you need to see is on the graphing, you have to get to the close to 62.5 as a volume, and then the graph goes something like that, right? So you need to see the any of the x that reach to the 62.5. And then this is the axis you're looking for. So use a graphing calculator too. So same thing as a B, use your graphing calculator to solve the length of the side of the square cutout. If the volume is now 23 equal to 11 minus 2x and 8 point minus 2x times of x. And then you'll see that too. So now 23, but there's a two place of the 23. So about 23 is right here. So it could be this x and this x, okay? So here or here. So you'll see two places of the x that give you the volume of the 23. And then C, using the graph calculator, find the approximation maximum value of the box of the volume. So maximum place is right here, right? So maximum place. So what place is this? Okay, so you will see approximate that. And then using the graphing calculator to solve the length of the side of the square cutout to produce the maximum value of the you found the x. So now you gotta find the what x is gonna be to give you the maximum volumes, okay? So the way that I found it, and then number 5a, I got x equal to 1.1746. And there's another x also show that the volume is 62.5, it is 2.0333. And for the x's I found it is 0.277 and 3.439. And then the maximum volume that I found from here is 66.15. And then the x that related is 1.585. Okay, so when the cutout was 1.585 inches, and that give us the maximum volume of the box. Okay, thank you for listening.